Hey, what's going on, science and cooking class? Greg, one of your TFs here, and I just want to talk to you a little bit about solid nitrogen. That's what you're seeing a picture of here, is solid nitrogen. Um, so if you remember in Dave Arnold's lecture, he actually made solid nitrogen. What he did was he poured in liquid nitrogen into a beaker or a test tube, and then he put a tube on it and attached it to a machine, and the machine made a bunch of noise. It sucked out a bunch of the air, and the liquid nitrogen became solid nitrogen. And while he was doing that, he mentioned something called evaporative cooling. So that's what I want to talk to you about today. I want to answer the question, what is evaporative cooling? So you know about vapor. When you get coffee or something, you have evaporation. The vapor is some of the water molecules leaving, and so you know that things are getting cooler. There is some sort of evaporative cooling, because it's really scaldingly hot when you first get it, and then eventually it's drinkable, and then it's disgustingly cold. And so I want to think a little bit more scientifically about what this evaporative cooling, how it works. So let's say you have your liquid, it's tea or coffee or water, something like that, and so what's going on inside of here? So you have a bunch of just water particles, just water molecules bouncing around. I'll just draw them as these dots with little arrows on them because they're just moving around, bouncing in different directions. And so there's some slow-moving ones, but also let's draw some faster-moving ones. So I'll draw them as bigger pink arrows because they have a bigger velocity. So you got these big pink arrows, and maybe a big pink arrow, which is a quick-moving water molecule, will bounce into one of these slower-moving ones, and then it becomes a big-moving water molecule or a fast-moving water molecule. And so they're all bouncing around, and when you're inside the liquid down here, it's just, they're kind of all just bustling about, and nothing really interesting happens. But what happens if you're up here by the surface? So, for example, if you have one of these slow-moving water molecules by the surface, and he starts to move up. What happens there? Well, gravity's fighting him back down, but also don't forget you have air particles. So there's some air particles just bouncing about in all these different directions. And maybe one of these air particles comes and it hits into the water molecule, and the water molecule just bounces back in. And that happens a lot. But if instead of having one of the slow-moving water molecules, you have one of the fast ones, and he starts moving this direction, then it could be going faster than the air particles. And the air particles, if they go and they bounce into it, it doesn't really affect it that much, and it can escape. And so a bunch of the fast-moving water molecules can just escape. They're all escaping, and then so now they're up here in the air, and that's your vapor. It's the water molecules that were moving really quickly near the surface. And so since these fast-moving water molecules are now escaping and the slow ones are still in the liquid, the average temperature goes down. There's less energy in there because the energetic particles left. Now, what did Dave Arnold do? Dave Arnold, he closed this thing off. So he took some tube or something like that, and he closed it off, and then he made a vacuum out here. So he started sucking. He sucked out all the air particles. So all these air particles now get sucked out. And so what happens is that the fast-moving particles, the vapor that was up here, it now is being sucked out. And so there's not as much stuff going on down here. There aren't these air particles. They're gone, and there aren't these guys that are all being sucked out. So that makes it easier for the fast-moving particles to escape, and it also, some of the slower-moving particles will also escape, but still more of the fast ones will escape. And so you're doing the same thing as before. You're cooling, except for now it's just easier because there's nothing in the way really here. So they escape, and so that just it cools quicker, and so you can cool down the liquid nitrogen, and it can become solid nitrogen. Okay. So there's just one last thing I want to show you, and it's a cool little applet about evaporative cooling. So what I'm showing here is this is just a freeze frame of a bunch of fast-moving particles in a little bucket here, or a beaker. and so they're really hot. And I'm going to hit play in a second, and we're going to see what happens. And by the way, so this little arrow here is the temperature, which kind of is telling you the average energy of all the particles here in the beaker. And so let's see what happens to this hot bunch of particles when we let them bounce around. Okay, look at the temperature. It's going down because the all the fast-moving particles are escaping. And so what we have going on here, so there aren't any air particles here, but you still have gravity keeping these guys down. And so the fast-moving particles have enough energy to beat that gravity and escape. And so you can play with this thing a little bit. You can take the URL here and play with it a little bit. This is actually an applet for something called Bose-Einstein condensate, but don't worry about that. The important thing is that this thing is getting cooler, and so the hot particles are escaping, and we have evaporative cooling, and you can play with the size of the beaker. And so these guys are leaving, and so it's kind of fun to play with it and watch the temperature go down as things evaporate, or you can get sick of this whole business and just get rid of all the particles too, and be done. Anyway, it's been a good time. Thanks for listening, and if you have any questions, feel free to email me. Thanks a lot.